Praise be to God, and peace and blessings be upon the messenger of God, our master Muhammad, and upon his family and all his companions. Then after that, by time indeed, mankind is in loss, except for those who have believed and done righteous deeds, and advise one another to truth, and advise one another to patience. In the name of God, the most gracious, the most merciful, we begin this course on differential protection, so stay with us. Inspiring the renaissance of our nation. The differential protection course is recommended for testing and commissioning engineers, as well as maintenance and operation engineers, in addition to design engineers, whether they are experienced professionals or even new engineers, along with university students in their final stages to better understand the job market practically. This course will, God willing, serve as a reference for solving many problems related to the incorrect application of protections. Why seek alternatives to overcurrent protection? It's simple but insufficient for all power system needs. Time coordination is tough in complex networks. Clearing time rises near the source, risking stations and network stability during faults. In this diagram, clearing time increases near the source. A fault here means 700 minutes clearing time, high for coordination. If faulted, the relay trips in 100 minutes. We face difficulties applying the principle for several reasons, including challenges in time coordination. In the previous course, we noticed the clearing time increases as we approach the source, posing risks to generation and transformation stations and impacting network stability. When a fault occurs, observe the time grading. Clearing time rises near the source. In this area, clearing time is 700 milliseconds. If the fault is here, relay R should trip in 100 milliseconds. If R fails, relay H should trip. When a fault occurs, all three relays sense it and issue a start signal simultaneously, starting the tripping countdown together. When a fault occurs, clearing time rises near the source. Here, clearing time is 700 millilapses, high for coordination. Relay R trips in 100 max here. If R fails, H trips, then G. All relays sense the fault. Timers start together. If R fails in 100, H trips in 300 ms, not 400, as timers start together, giving R 100 ms grace. So if relay R does not trip, then relay H should trip. If H does not trip, then the relay further away, G, should trip. This process happens gradually. Notice that when a fault occurs in this area, all three relays will sense this fault. And so all three relays will issue a start signal at the same moment. This means that the countdown for the tripping time of the three relays will begin simultaneously. If relay R does not trip after 100 milliseconds, then relay H will trip after 300 milliseconds, not 400, because we mentioned that all the timers started at the same moment, as if relay H gave relay R a grace period of 100 milliseconds to issue its trip signal to the circuit breaker. The circuit breaker R, or relay R, will trip after 100 milliseconds, and then relay H will trip after 300 milliseconds, not 400, because we mentioned that all the timers started at the same moment, as if relay H gave relay R a grace period of 100 milliseconds to issue its trip signal to the circuit breaker. Overcurrent relays can't pinpoint fault locations in transformers. They detect faults when current exceeds a set value. In short circuits, distinguishing fault current values between sections is challenging. The relay indicates a fault but doesn't identify the exact location or affected element. These limitations led to unit protection, protecting specific zones in the electrical network independently. These relays detect faults when current exceeds 60. In short circuits, the overcurrent relay struggles to differentiate fault current values between sections. It indicates a fault but can't pinpoint the exact location. Is it on the transformer, capacitors, or motors? These challenges led to the search for a new protection method, resulting in unit protection, which protects a specific zone independently. This method compares electrical quantities. The operation principle relies on determining the fault current's direction by comparing values at each zone's start and end. Is it on the transformer, the capacitors, or the motors? These issues were the reason for the search for a different protection method, leading to unit protection, protecting a specific network area independently. This involves comparing electrical quantities, current or voltage, at the start and end of the protected area. The operation principle relies on determining the fault current direction by comparing values at the start and end of each zone. Any protection comparing electrical quantities, current or voltage, between the beginning and end of the protected area is referred to as such. Determining fault current direction by comparing values at each zone start and both in magnitude and direction is key. We must agree on the term direction as our course foundation. Current out of bus bar to feeder is positive. Out of feeder to bus bar is negative. Implementation. It's principle. This is a key factor for many protection systems. We must agree on the term direction as a foundation for this course. Current flowing out of the bus bar to the feeder is positive. From the feeder to the bus bar is negative. In the image, current out of bus bar G is positive, into bus bar H is negative. Currents feeding the fault area in line HG are positive as they flow out of the bus bar into the faulty feeder. If positive current entering the line is 1 ampere at 0 degrees, the negative current out is 1 ampere at 180 degrees. Resultant currents are 1 minus 1, or 1 at 0 plus 1 at 180 degrees, totaling 0. Current entering the protected zone is positive, out is negative. Thus, currents in healthy section GH total 0, while in fault section HG, they total 2 amperes. Positive current entering the line is 1 ampere at 0 degrees. Negative current exiting is 1 ampere at 180 degrees. Resultant currents are 1 minus 1, or 1 at 0 degrees plus 1 at 180 degrees, totaling 0. Current entering the protected zone is positive. Exiting is negative. Total current in healthy section GH is 0. In section HG, where the fault is, it is 2 amperes. This rule aligns with global systems for electrical network analysis, emphasizing polarity's role in current flow direction. Both resultant currents will remain 0. The current entering the protected zone is positive, while the current leaving is negative. Thus, the total current in the healthy section GH is 0, while in section HG, where the fault occurred, it is 2 amperes. Neglecting this rule can cause problems during stability tests. This rule aligns with global systems for electrical network analysis. Incorrect polarity causes the relay to misinterpret currents. CT placement determines the start and end of each protection zone. Ignoring this rule causes issues in stability tests, especially in defining protected area boundaries. This rule aligns with global systems for electrical network analysis, highlighting the importance of polarity in current flow direction. If the polarity is incorrect, the relay will consider all incoming currents as outgoing and all outgoing currents as incoming. CT placement determines each protection zone's start and end. This CT monitors all currents in the protected zone, so its placement must be strategic for overlapping protection. If the polarity is incorrect, the relay will consider all incoming currents as outgoing and all outgoing currents as incoming. CT placement determines each protection zone's start and end. In addition, this CT is the one that monitors all the currents entering and exiting this protected zone. So the location of the CT installation must be determined in a strategic way so that it achieves overlapping protection in the different protection areas. Inspiring the Nadet Watan. Differential protection is considered one form of unit protection, characterized by its ability to distinguish faults occurring within the protected area from those outside it. So we can say that differential protection is unit protection, but we cannot say that all unit protection is differential protection. What is it? One of the forms is the one that relies on protection lines are vital. This course covers protection for generators, transformers, bus bars, and lines. Differential relays activate only for internal faults. Transformer faults cut power via its relay. Line faults are isolated by opening breakers. Bus bar faults disconnect feeders. The differential relay should operate only if a fault is within the protected area, not outside it. For transformer faults, the relay cuts power by opening circuit breakers on both voltage sides. For line faults, the line's differential protection isolates the line by opening local and remote breakers. For bus bar faults, the bus bar's protection disconnects all potential feeders. These protections are independent. Generator protection differs in two ways. Firstly, the protection system, including the circuit breaker, is placed at the cable's start. If a fault occurs before the breaker, it opens to isolate the cable. If a fault occurs on the line, the differential protection isolates the line and cuts off power by opening circuit breakers. For bus bar faults, the differential protection disconnects all feeders that could supply the fault. These protections are independent. Generator protection has two peculiarities. First, cable protection places the circuit breaker at the start of the cable, opening for faults ahead. In contrast, generator protection trips for faults behind the breaker. Second, any network fault is isolated by opening the breaker. Each protection is independent. For generator protection, two key differences exist. First, unlike cables where the circuit breaker is at the start, for generators, it trips for faults behind it. Second, opening a generator's breaker doesn't isolate the fault. Power from the generator continues, unlike other network elements where faults are isolated immediately. For generator protection, the circuit breaker trips differently. If a fault occurs, the breaker opens to isolate it. However, for generators, opening the breaker doesn't isolate the fault. It persists. The solution is to trip the breaker and simultaneously disconnect the turbine and perform an emergency shutdown of the exciter. In the case of the generator, simply tripping the circuit breaker will not isolate the fault. The fault will continue even after the generator circuit breaker is opened. This is because once the breaker in front of the generator is opened, the power supply to the fault from the network side will be isolated, but the power supply to the fault will remain active from the generator side. This is contrary to the protection of all other elements in the network, which are secured and isolated at the moment of the fault. As soon as the circuit breaker is opened, in the case of generator protection, if the circuit breaker is tripped, the turbine must also be disconnected at the same time, and an emergency shutdown for the exciter must be performed. Otherwise, the fault will continue to be fed from the generator's windings that are still spinning and generating electricity. We want to point out that the term unit protection in the American standard refers specifically to the protection provided for the generator only. In contrast, in the European standard, the term unit protection refers to the protection of a unit or element in the electrical network, whether it is a line, transformer, busbar, motors, or others. Differential protection was effectively implemented at the end of the 19th century and was one of the first electrical protection systems used ever. When we say differential relay, its translation in Arabic is al-marhala tafaduli or al-marhala al-farqi, noting that Arabic references have varied in translating the word relay. Some say it's a relay, meaning it transmits the tripping signal to the circuit breaker. Others say it's a handler, meaning it hands over or gives the tripping signal to the circuit breaker. Some have called it a completer, which completes the tripping process to the circuit breaker. The differences create beauty, and what's important is that the common points remain the focus of attention. Whether it's a relay, handler, or completer, judge by meaning, not names. In Arabic, differential relay translates to al-marhal al-farqi, a literal translation. Difference and subtraction differ. Subtracting 5 from 4 gives -1, but the difference is 1. The difference is the absolute value of subtraction, meaning the result is always positive. What is the result of subtracting 5 from 4? You would answer that it is -1. However, if I ask you what the difference between 4 and 5 is, you would say it is 1. So, the difference between difference and subtraction lies in the negative sign, as if we are saying that the difference is the absolute value of the result of the subtraction. And if I mention the term absolute value, it means that the result should always be positive, and the sign is not important to me. So, from the definition of the word differential, we can conclude two things. First, that there is a comparison between two values, and second, that the result of this comparison should be positive. This means that we are not concerned with which of the two values is greater than the other, but rather with the difference between them. Differential protection works by comparing incoming and outgoing currents in a protected area, based on Kirchhoff's first law. Incoming currents must equal outgoing currents. Any difference indicates a fault. This difference is the differential or operating current. The current balanced differential relay uses this principle. Voltage balanced differential relays, which measure voltage instead of current, are rarely used today and will be discussed later. Normally, incoming and outgoing currents should balance, making the differential current 0. If outgoing currents differ from incoming ones, the difference is the differential or operating current. This relay is the current balanced differential relay. Other differential protections measure voltage, known as voltage balanced differential relays, which are rarely used today. Normally, the sum of currents entering a point equals those leaving, so the differential current should be 0. The sum refers to the vector sum, considering magnitude and direction. Some relays use a vector sum to find the differential current, while others subtract it. These are rarely used nowadays, and we will discuss them later when we talk about the current balanced differential relay. Normally, the sum of currents entering a point equals the sum leaving it, making the differential current ideally 0. Sum of currents refers to the vector sum, considering both magnitude and direction. An engineer once told me some relays perform a vector sum to determine the differential current, while others subtract it. This is incorrect. All relays perform a vector summation to find the differential current. If a fault occurs within the protected area, the incoming current will differ from the outgoing current in magnitude and direction, creating the differential current. Sum of internal and external currents means vector summation, focusing on magnitude and direction, not algebraic summation. And this is wrong. All relays perform a vector summation to find the value of the differential current. In the event of a fault occurring within the area to be protected, the incoming current will differ from the outgoing current, which will create a difference that leads to what we call the differential current. If this differential current exceeds the relay setting, it will cause the differential relay to trip. If the vector sum of the currents is greater than the relay setting, then issue a differential trip signal. Thus, differential current indicates internal faults. If the sum of the currents is greater than the diff setting, issue a trip signal. Differential current indicates internal faults. We set the diff setting to increase safety and avoid false trips due to CT errors. Higher setting value decreases sensitivity, lower value increases it. Theoretically, but we have set the differential current setting to increase safety and to avoid any false operation or incorrect tripping of the relay due to various practical issues, such as CT errors, for example, which we will explain in detail in the upcoming episodes. Increasing the value of this setting means a decrease in the sensitivity of the relay, while decreasing the value of this setting is equivalent to increasing its sensitivity. Applying the idea of differential protection in practice is simple when the parts to be protected are confined to a specific area, like a generator, transformer, or bus bar, and when the CTs on both ends are close to each other. In this case, all the CT wires are connected directly to the relay. However, in the case of high voltage cables or overhead lines, we connect the local CT directly to the relay and have to transfer the measured currents from the other end over long distances to compare them. This current transfer is done using what is called pilot wire, which is connected to the relay and is used for distances that can reach up to measured from the other end over long distances so we can compare them. These planes are transferred to the other side using what is called pilot wire, which is connected to the relay and is used for distances up to about 25 kilometers. In modern differential protection relays, it has become possible to use what is called digital communication, which utilizes fiber optic cables for distances that can reach up to approximately 100 kilometers. High impedance differential protection is a special and different type of differential protection where we connect a high resistance in series with it. The purpose of placing this resistance in series is to help achieve high stability for the protection system, especially when an external fault occurs that causes one of the CTs to enter saturation. This type of protection is typically used with generators, bus bars, transformers, reactors, and even motors, where all the CTs are directly connected to the relay. However, one of its downsides is that all the CTs connected to it must be identical in all specifications. The goal of this episode is to explain the principle of differential protection and to give an overview covered later. Next, we discuss the history of relay development and their classification by technology into types. We explore technology limitations and capabilities. Stay tuned. Electromechanical, static, digital, and imaging. We will delve into understanding the limitations imposed by this technology, which have led to varying capabilities. So stay with us, and we'll see you soon.